This is MATHguide.com, and my name is Mark Karadimos. Greetings! In this video, you're going to learn about continuity. And in this video, specifically, we're going to look at a textbook definition, and then I'm going to talk about a graphical way of looking at this. Let's get started. So here's the textbook definition. Oh yeah, you look at this definition and you're trying to make heads or tail of it. So first of all, it says a function is continuous on this interval. So in other words, we're not even looking at the whole function. We're just looking at the piece of the function. And so if you go from A to C, A of course being less than C, and you're looking at the interval of some function, and you're thinking, well, what's the limit as you approach some value B? And by the way, B is going to be some value between A and C. So in other words, you've got this little snippet of a function, and B is some limit that you're approaching within the confines of that little snippet. Okay, so you've got the snippet, we're finding a limit. Now, what does this definition say? This definition says that your answer to the limit has to be the same as if you're evaluating the function at the value B. Yeah, it's clear as mud, isn't it? Yeah, and most things happen like this in calculus and even in mathematics in general. You've got this really simple looking equation, and what you're trying to do is to make heads or tails of it. So you're trying to figure out, what the heck does this mean? And the only way to really figure out what this thing means is to look at some situations. Okay, now I'm going to show you two situations that it's going to make this abundantly clear. Let's take a look at them. Here we have a function drawn for us, and this function is defined from A to C, so it's on the interval from A to C. And you'll notice that this function is kind of quirky because there's a hole in the graph and there's a filled in circle directly beneath it. Now, we're going to find the limit, of course, across the entire interval, but if you just take a look at B, let's say, is the x value where the hole and the closed circle are contained. So if you recall the definition of continuity, what we're going to do now is we're going to find the limit, right? So let's find the limit. So if you are finding the limit as you're over here on the left side and you're approaching the curve, you're headed towards this point. And of course that means the limit is E. Okay, so the y value that you're approaching is E. All right, but let's say you're on the right side of B and you're finding the limit. If you're finding the limit here on the right side, you're still headed towards this open circle, and that open circle has a y value of E. So clearly you could see that when you're finding the limit at B, or as you're approaching B, that is, when you're finding the limit, you could see that you're approaching the y value E. All right, but now if you evaluate the function and you say, all right, well, what is the value of the function when your x value is B? Well, it's right there. Okay, so it turns out that when you're finding the limit is E as you're approaching B, but when you evaluate the function, we could see that we evaluate the function, we get D. And those two values are not equal. Now, according to the definition, ding, okay, that definition says they have to be equal in order for this to be a continuous function. So therefore, we say this function is not continuous. All right, let's take a look at another example. All right, we have another function that has been drawn, and it is defined on the interval from A to C. Now, g of x here is kind of quizzical because right here it has some concern, and the concern is, let's say it's at the value B. There is a closed circle beneath an open circle, and let's now take a look at this function, and let's take a look at it in light of the definition for continuity. So ding, there it is. Okay, so we've got the definition to look at. So the first thing it asks us to do in the definition is to find the limit as we approach B. Now remember, we're finding the limit everywhere along the curve, but or along this interval. The concern is at this location where there's an open and closed circle. So that's why I'm specifically looking at this b value, where this closed circle is located. So when we find the limit as we approach this value b from the left side, you can see that we're approaching this open circle, and that has a y value of e. So from the left side, we find the limit is e. Now from the right side, we approach this value b, right, this x value b, but the y value is approaching d, right? It's a different location, right? So from the left, when I find the limit, I'm approaching e. When I approach b from the right side, I approach the y value d. I'm getting two different values. That means the limit as x approaches b does not exist. Okay? Now let's evaluate the function. If you evaluate the function at x equals b, the answer is d. All right? So when x is b, y is d. Now when we did the limit says it doesn't exist because I'm getting two different values from two different sides. And then when I evaluate the function, I get d. If this is a continuous function, the limit and the evaluation are supposed to be the same, and they're not. So therefore, this is also a function that is not continuous, or sometimes it's called a discontinuous curve. Are you confused by this? Yeah, no kidding. This textbook definition is thick. So instead, let's take a look at a graphical explanation. All right, so here are the two examples that we looked at. And when you're looking at these two curves, the reason why these two curves are not continuous is because one of them has a hole in the curve. Yep, that top one, f of x, has a hole. Any curve that has a hole, it's not continuous. G of x, notice it has a jump, right? It's a jump. As you're looking at the curve, right, and you're reading it from left to right, just take a look. I'm reading it, jump down. Okay, now I gotta continue on to the right side. So any curve that has a jump is also not continuous. So curves with holes and jumps are not continuous. So far you've only seen functions that are not continuous. So it's only fair to you to be able to see some that are continuous functions. So for instance, if you were to see a function like a polynomial can be graphed with one sweep of your pen or pencil, and you don't have to lift your pen off the paper to put it back down again and then to draw a remainder. In other words, there's no holes or jumps. Okay, so a polynomial function, they're all continuous. Sine function, continuous. So any function that can be drawn like that, like a logistic function, square function, many functions like that. Okay, there you go. So that's the simple explanation. All right, well, make sure you go to MATHguide.com and literally check out our hundreds of lessons, our instructional videos, and interactive quizzes. Take care. Continuous. No break, no holes in the curve. It's one continuous function. There's a reason why math people choose these words, right?